Hello again, everyone. So in this lesson, we're going to go over beginning of bond hybridization. This is quite a lengthy topic. I am cutting a few things out of our next lesson, but this really sets the stage for that. So I will break this apart into two different videos. So we're going to have part one of bond hybridization day one and part two of bond hybridization day one. Okay, so let's get started. All right. Before we do, like a lot of things we've seen in this unit, it seems to be a theme. What was originally thought to be true at one point, upon further discovery, upon further study, noticed that this wasn't actually the case. So this question we would have asked in class: what is, and it's also a good review of Vesper. What is the Vesper shape around any carbon atom? So any of these carbon atoms, you know this to be benzene. Um, any of these carbon atoms would have, hopefully you'll take a moment here where you can figure that out yourself. We have one ligand here, one ligand here, one ligand here. Yes, although it is a double bond here and a single bond here and here, they still all count as just one ligand each. There are no lone pairs around these carbons, so we know that this is going to be, hopefully you're thinking to yourself, or you've answered this, it is trigonal planar, right? So then next question, which is a bit of an extension now, what if you were asked to predict where the electron density might be? Now you have a bit of background in this, having talked about polarity last year, but where do you think you would find more electrons? Essentially, is what it's asking. Where would you have a greater electron density? Around this benzene ring. Now, like most scientists at the time, you would have said, well, it's going to be more around these double bonds. You'll have more electrons here and more electrons there and there, and there will be less here. So that's what was predicted. That's what Vesper helped them to predict as well. But this was discovered instead. So this is a symbol, or a rather a computer generated image of the electron density around benzene, and we can see that we don't have any kind of, let's switch to a highlighter here. maybe purple would be best. So instead of seeing areas of alternating electron densities, right, we don't see that. We instead see a pretty uniform distribution of electrons all throughout. Right, now that doesn't align with what was expected. So Vesper correct, but not entirely complete. Again, we saw that it wasn't completely, or rather, it was uniform throughout. It wasn't alternating as was expected. So this caused some confusion, led to an improvement or an addition to Vesper theory. Okay, now let's go back a bit. All right. So a single hydrogen has one electron in the 1s orbital. Another hydrogen has the same one electron in the 1s orbital. Both are spinning up, or have a positive half fourth quantum number, magnetic spin number. Right? When they create H2, this is what happens. Both are going to be spinning in the up direction. So this electron right here has a spin up. But if you have two of these hydrogens, so one hydrogen here, they will create a bond, right? A covalent bond. Now, that just means that one electron is going to directly overlap with another electron, but this is not going to happen. So this is not going to be the case. You won't ever have two electrons with the same quantum numbers, right? 1s spinning in the same direction, right? So that can't happen. I'm going to put this one back. One of these electrons, they were originally, right? They were both spinning in the up direction. One of them is going to then spin down, so that in this covalent bond, nonpolar covalent bond between the two hydrogens, the two electrons that make up this bond, one will be spinning up and the other one will be spinning down. And that's how they form that bond. Right? And this is called the valence bond theory. So the electrons that are in the valence shell will overlap, and they will need to have opposite spins to create these bonds. Right? Okay, this opposite spinning is going to ensure that Pauli's exclusion principle applies and that it is not violated, where we could not have two electrons spinning in the up direction. We have to have one up and one down, or clockwise and counterclockwise. Okay, the other thing two hydrogen atoms form covalent bonds. When they do that in the s orbital, they do that only with partially filled orbitals. So let's go back. Notice that the 1s orbital is partially filled. This 1s orbital is partially filled. See, that just means there's one electron here and one electron here. Those are the only kinds of suborbitals that can create these covalent bonds. That will make more sense. We're going to get to an example, and this is it. All right, so I've started to write the energy level diagrams as review as well to help you out with that. The energy level diagram for chlorine has been mostly filled out, but I'm missing our valences here. So let's add them in. We know that chlorine is a halogen, and along the 3p suborbital, it has 5 electrons. So first, spin up. So spin up, spin up, spin up, right? Singly first. We still need to add 2 more electrons, but those will be added in the opposite spin. So this is the X orientation that we finally completely filled, and this is the Y orientation, right? So this is the energy level diagram for chlorine. Okay, now it being this chlorine having to then just use the valence electrons, we can only let's refill this orbital diagram with only valence electrons. So the 1s orbital has 2 electrons, spin up and spin down. The 3p orbital has spin up, spin up, spin up, and then 2 spin downs for a total of 5 in the p and 2 in the s for 7 electrons in total. And this is its electron configuration: 3s2, 3p5. Right? If you add the exponents, it'll give you 7, and here are those 7 electrons. Hydrogen's a little bit easier, right? Hydrogen just has that 1 electron spinning up, right? So these are the valence electrons, orbital diagrams for the valence electrons for both chlorine and hydrogen. Now we're going to see how they come together to create hydrogen chloride. Again, this was mentioned earlier, but an important point. Bonds can only form with a half-filled suborbital. Okay, here's an example. Here's how that looks like. So hydrogen in this 1s orbital has 1 electron spinning the up direction. Chlorine, if we go back to our orbital diagrams, all of this is 3p, but we know that this is 3px, and this is 3py, and this is 3pz, right? A bond cannot be made with this completely filled suborbital. A bond can't be made either here, so x and y, they can't form bonds. The only suborbital that can create a bond is 3pz because it's half filled. Again, only half-filled suborbitals can create these bonds. So this is the 3pz electron. So this is the 3pz electron, and it's also spinning currently in the up direction. When they combine, we have a spin up and we'll have a spin down. The spin will change. They will be opposite. Does it matter which one changes to flips up or down for our purposes? No, for our purposes in this course, it does not matter. So choose any electron. Okay, that's how, leaving out an important point that we're getting to right now, but this is essentially how bonds are formed, right? So far, two main things to consider. Just your valence electrons are going to be involved, right? Also, you can have only half-filled, try to write a bit neater here, only half-filled suborbitals are going to be involved in creating these bonds. Okay. Right, so to add to the Vesper theory, what's called hybrid orbitals had to come into play. So this is our first example. Methane, CH4, has one ligand here, one ligand there, one here, and one here. Right? If we're thinking back at Vesper, this is going to be tetrahedral, right? Its energy level diagram, so carbon central atom, carbon's energy level diagram looks like this. 1s has 2 electrons, but it's not really involved it's not involved in bonding, right? So we're only considering these electrons. So in the valence electrons, we have this suborbital. This suborbital is completely filled, right? So that, so far at this point, is not going to be involved in creating a bond. The only suborbitals that can create bonds then are the 2px and the 2py. But look, we don't have just 2 bonds. We have 4. We need 4. We only have 2 in this case. So what happens to the ground state? So this is our ground state configuration of electrons depicted in this energy level diagram. We need to then, to create 4, because we have 4 bonds, to create 4 half-filled suborbitals, we need to promote. It's a bit hard to see here, but I will fill it in. We're going to promote one of those s electrons. So one of the 2 s electrons is going to go into the 2pz, and what that creates is the situation that we want. We want there to be 1, 2, 3, 4 half-filled suborbitals to create these 4 bonds with hydrogen. So we're almost there. um, Ignoring the writing in blue, I'm going to write what that looks like. So after, this is our excited state now. So that was our ground state at the beginning. This is now our excited state, this promotion of electrons, higher energy, right? We have single electrons existing at different energy, slightly different energy levels. So to minimize that, we need to draw what's called a hybrid state. And it looks very similar. I'm going to call it my hybrid state, and I'll just write H for that. Have 1, 2, 3, 4. Because, going back, we have 4, 1, 2, 3, 4 suborbitals, but it's no longer 2s, 2px, 2py, 2pz. It's 1 electron from an s, so there's 1 electron from an s, there's another electron from a p, another electron from a p, and another electron from a p. So it's going to be s, because of the 1 electron, p, 3, because we had 3 electrons from p, so it'll be sp3. So our hybrid state is no longer what the excited state shows us. It's sp3. It's no longer 2s, 2px, 2py, 2pz. It's simply sp3. They've hybridized. These orbitals, or these suborbitals, have hybridized. We now have an electron here, 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 and the 4th one there. They're now ready to create those bonds. They also change their shape. So instead of having what we once had here, a spherical shape and then 3 dumbbell shapes in 3 different orientations, they merge to create a new shape that looks like this. 1, 2, 3, 4. Right? A bit more, think of a dumbbell, it's a bit more circular. Imagine these dumbbell shapes merging with a spherical shape for that s electron. Now, finally, we have hydrogen and its electrons. So 1 hydrogen here, 1 hydrogen here, and so on. These 4 electrons, these 4 hydrogens, they then directly overlap. They collide with each other to create our covalent bonds. This one, let's say, connects here. This one completely collides there. That one here, and this one here. And it will then look like this. So this is the true shape of a methane molecule. And we see that it was created from the hybridized states of carbon, sp3, in their sp3 form, and the 1s electron from hydrogen. One more thing to say, by creating these covalent bonds, we have 1 electron spinning up here, another one spinning down. Here the same. We have 1 electron spinning up, 1 down, up and down, and last set up and down. Okay, now let's look at beryllium hydride. Okay, so this is the ground state, so I'll label that as G, the ground state orbital diagram for beryllium, 2s. We know that beryllium is going to need to have 2 bonds because of BeH2, right? So it doesn't have any half-filled suborbitals. Look, none here, no electrons here, and a completely filled orbital here. So it can't create a bond. So in order to do that, we have to promote. We promote an electron, and then that will look like this. We'll have a 2s electron here, That is this electron. We'll have another, what used to be a 2s promoted to 2p. In this case, it's in the 2px suborbital. When it hybridizes, so you can think of this as the excited state, when it hybridizes, you get this hybridized state. Look like this, and that's called sp because there's one electron that came from s and one that came from p. That's sp. Think of it as having just exponents, but of course you don't have to write that because they're just ones. So there you go. Okay, that is part one. Take your break here. Take home messages are, I'll add a slide to that. Okay, take home messages, or the main ideas for this is only valence electrons are involved in bonding. I'm going to repeat the same 2 points. Only half filled suborbitals are involved in bonding, not completely filled and not empties. Third thing, electrons can get promoted to create the half-filled suborbitals. Okay, that's your take-home message for this half, right? Next video, we'll go over other kinds of hybridized states.